Hello students, welcome to the EPG Pathshala. I am Sumalay Roy from Department of Physics and Astrophysics of Delhi University. Today we are going to discuss about the module, the time-dependent Schrodinger equation, conservation of probability and continuity equation. This is from the paper Quantum Mechanics. In the earlier module, we introduced the concept of wave function to describe the properties of a physical system. We learned that in the position representation, the wave function psi of a particle is a function of its space coordinate r and of time t. In this module, we are concerned with the non-relativistic motion of a free particle as well as that of a particle in a force field that can be represented by a potential energy. A quantitative description of the motion in terms of differential equation, the Schrodinger equation, is developed. In developing this equation, we are guided by the principle 1, that it should be linear and homogeneous equation so that superposition principle holds. Number 2, the results obtained by using the equation should agree with those of classical mechanics in macroscopic situations in accordance with the correspondence principle. And number 3, the equation should be of first order in time derivative so that the evolution of the system is entirely determined once the wave function is known at a particular time. Using the definition of position probability density and the condition that the probability of finding the particle somewhere at time t is unity, we deduce the equation for conservation of probability, leading to the equation of continuity. In the treatment presented, we have only tried to make it plausible. In fact, as we shall see in the subsequent study, the successful application of Schrodinger's equation to a variety of problems and the comparison of its predictions with experimental data, which demonstrates its correctness in non-relativistic quantum mechanics. This is the well-known time-dependent Schrodinger wave equation proposed by Schrodinger to describe the motion of a particle moving in a potential V. This is a basic equation of non-relativistic quantum mechanics, which we should point out cannot be proved like Newton's law in classical mechanics. Probability conservation and the hermeticity of the Hamiltonian. Let us ask, how does the probability density change with time? The interpretation of modulus square of the wave function psi rt as position probability density requires that the probability of finding the particle somewhere in the space enclosed must remain unity as time changes. That is to say, that probability is conserved. Once psi RT is normalized according to the equation integral modular square of psi RT modular square dr equals to 1. It must remain the same at all times. Therefore, the normalization integral must be independent of time. That is, del t integral of p RT dr is equal to 0. This condition, requiring the conservation in time of normalization of the wave function, also implies that the Hamiltonian h hat equals to minus h bar square by 2m del square plus v RT, which is again equal to 1 upon 2m p hat square plus v equal to t hat plus v of the particle in a real potential VRT is a Hermitian operator. Admissibility conditions on the wave functions. To address the question as to what kinds of mathematical functions are acceptable as wave functions for a particle in quantum mechanics, we find that the probability interpretation of the wave function makes it necessary that psi must satisfy certain general criteria. In order to ensure that modulus of psi squared d tau for an infinitesimal volume element d tau should lie between 0 and 1. We require that psi should be one finite and number two single valued. Single valuedness is the requirement that at any point the wave function should have a unique value, so that the probability should not only be finite but also uniquely defined. Another property which is required of the wave function is that psi and its partial derivatives, which are del psi del x, del psi del y, and del psi del z, should be continuous function of R for all values of R. This requirement arises from the fact that the potential function is supposed to be a continuous function of R, except perhaps for a certain number of finite discontinuities. This condition is therefore necessary for the consistency of the Schrodinger equation. In this module, we have learned how to develop the time-dependent Schrodinger equation for a free particle, also for a particle moving in a field of force. We have learned the three-dimensional generalization of Schrodinger equation. We have learned to express the Schrodinger equation in operator form. We have learned how the normalization condition on the wave function leads to conservation of probability and continuity equation. We know the admissibility criteria required for the Schrodinger wave equation. Thank you.